Today we are going to start working on diffusion in disordered systems. So we learned a lot about normal diffusion, about Einstein relation, about Fokker-Planck equations. But roughly in the early 70s, people started to notice that there are big deviations from normal Brownian motion. That means that the Gaussian central limit theorem does not work in real physical systems. That means that the diffusion is not normal, which means that the mean square displacement doesn't increase linearly in time, but increase like some t to some power alpha. So, and we are going to study one approach which is called continuous time random walks. We can say, roughly speaking, that this story began roughly in 1974 or 75 by some work of, this is not good, by two people. They are called Scher and Montrol. 1974, I believe. Scher is now working in Weizmann Institute. He's very old. I think he's not really working anymore. But at the time, he was working in a company called Xerox. Do you know what Xerox? What's this company called Xerox? You don't know. So Xerox is when Xerox machine is a machine like you have here when you photocopy, you put the paper in the machine and then there's a flashlight and then you get out the machine. It's a photocopying machine. And it was a very big company at that time. I guess now everything is done electronically, so it's not so important. But generally speaking, if you make a photocopy of some sheet of paper, what are you doing actually? Well, you are shining light and then there is some process and then you get out the photograph, right? That's a magic. So this company, Xerox, was looking at the following thing. They have a system which is, let's say, a semiconductor or some disordered metal, whatever. They come and they shine light. With some frequency. It doesn't really matter what is the frequency at the moment. When you shine light on a semiconductor, there are bands, electronic bands in the system. You excite an electron or a hole to some conduction band. So the idea of the light, this is a short pulse of light, is to excite some electrons, to start the process of movement. So you have suddenly, after you shine on the light, you have in the system some electrons, let's say, so these are electrons, and they are in this material. This material is very disordered. It's a very dirty system. So it's not like a lattice that every unit cell has the same atoms in it, but rather real materials, some organic junk inside, very complicated material. So now you have electrons. Now, what do you want to do is you want to transport these electrons from one side of the system to the other. So more precisely, maybe let's draw it like this. Let's say the flashlight is on this area of the material, and then you have many electrons. Of course, not only 5 electrons, you have a big number of electrons. They are here. Now, you want to move them. If you move them, you get a signal that, okay, there was a flashlight, and then you can measure them when they arrive somewhere. So in addition, you add this thing is a voltage drop, which means that there is an electric field in this direction. Now, this is, you can do this, this is called a time of flight experiment. What do I mean by time of flight? These electrons are going to move now because of the electric field, and they are going to go, and then you kind of remove them from the system. So there is a current in the system. So at time t equals 0, you start the process. You flash light, then you have some free electrons. Without the flashing of light, the electrons are tied so deeply in the traps that nothing happens. So you need to give them this push, small push at the beginning. And then they move, and then they come out on the other side. So you have a system, and the size of the system is L. This you can vary in the experiment. You can make it bigger, you can make it smaller. You can change the electric field, of course. You can play with all these games. And what do we expect? And actually, what is found in most ordered material? Ordered material means that a pure semiconductor, more or less pure. Maybe there are some small defects, but it doesn't matter. So you excite them at time t equals 0, and then there's an electric field, and then you measure the current. So, okay, there's an electric field. So you know what happens from Ohm's law, right? There's a current, right? Nothing very interesting. And because the system is finite, and afterwards you are draining the electrons that arrive in this boundary, you're just removing them, then you go down, and then there is some time t star, which is called the time of flight. This is the time the electrons moved from here to here. This, how fast this process is related in ordinary systems. It's related to how strong the electric field is, and how far is the distance between these electrons, where this light was, till the end. So if this distance is L, so you make L longer and longer, you have a constant velocity of these electrons inside the material somehow, due to all the collisions, etc. And then you can delay this by making L bigger. So this is controlled by L. This is essentially Ohm's law. You have a constant velocity. This is trivial because you have a constant voltage drop. Then, of course, these electrons are scattered by some usual Ohm mechanism. So instead of accelerating like Newton would predict, there is, of course, a friction, which is resistivity, and then, okay, you get this. Now, the people in Xerox, what they did, they wanted to check among thousands of materials. They wanted, for their purpose, to sell machines. They wanted to find the properties of different types of materials, all kinds of dirty semiconductors, dirty metals, whatever you want. They looked at everything. It's like Edison. You know how Edison found the light bulb? He just put different types of wires, and he just tried all of them until one of them was tungsten, and then he had light. But he tried many, many things before. So they did the same. Let's put here all kinds of materials, and let's see what will happen. And then what they want is, of course, let's say a good conductivity. So the current is high, then you can have a very small light, right? If the current is high, then it's enough to excite very few number of electrons, and then you will see this pulse, and then you will know it will die here, and then by the lengths, and you can say where something you can translate it into money by creating machines. But what happened to them was that they found that no, this was not the case in many, many materials, practically every disordered material. This is not found, and instead what they found is that the current is kind of decaying in time, and then there is a critical value maybe like T star, and then there is another decay. And this, what they found just by looking at many experiments. So this is the current versus time. Not a pulse shape, but which would be in constant velocity and you go out, but rather something like this and then like this. And this is described by T alpha minus 1 and then T minus alpha minus 1. This was an experimental observation, and alpha is between 0 and 1. So it means, you see, this is why it's going down. If alpha would be bigger than 1, it will go up. The current cannot go up. You start with some current, and then it goes down, and then it goes down. And importantly, it goes down, you see here, like power laws. And you see there are two exponents here. One is this starting part of the experiment, alpha minus 1, and then there's a second one, minus alpha minus 1. If you call this one, this exponent, all of this guy, you call psi, and you call all of this, you call beta, then the point is that this psi, this exponent here, psi plus beta, which you can measure, was always equal -2. Or usually they're minus psi and minus beta, but doesn't matter. So this was a universal number. Okay, so they found it, and then Scher was working in that. He was a theoretician, and they came to him, what is going on? Why do we get this? Etc. The experimentalists did first many experiments. For example, what is this alpha? So what did they do? They changed temperature, for example. And in some of the experiments, but not all, they found, that alpha, for example, is proportional to T or over some constant, which I'm going to call Tg. You can measure this alpha. So Scher and Montrol wanted to describe this by some random walk theory. Because what is the normal behavior? You see, you have here a usual velocity. Let us think what does this mean? The usual mindset of normal processes, as I mentioned before, this is the Ohm's law essentially here at the beginning. What is Ohm's law? Yeah, right? So Ohm's law, on the most basic high school level, in the language of random walks, I mean, you have random walkers in space, many of them, and then you have some bias into this direction, some electric field, a constant one. So what is happening here? You have some average X, an average drift. Of course, each individual one, there's a distribution of the displacements, etc., etc. It's much more complicated than this, but there is some average drift. This average drift, if the external field is weak, is proportional to the external field. That is Ohm's law, which means that it's proportional to the voltage drop, as you know. And this grows like T. I'm not looking at the prefactor. The prefactor is linear with the external field, but this is not my point. And then what do you have? You have V, some velocity. And V is simply the derivative. And what is the velocity? The derivative of T. This is a constant, independent of time. Right? So this is this constant. You see, it's independent of time. Of course, eventually, these guys will reach the boundary and be removed, so the number of electrons goes down. So this is proportional to the number of electrons also. But this is the usual way of thinking about transport. There is some constant, and this is, of course, the resistivity and mobility. And, of course, what this constant is a very complicated thing. I'm not saying it's something easy, but it's independent of time. So the first idea of Scher-Montrol is, okay, you have X, but it's not going linearly with T. Let's say it goes like T to some alpha. We need to understand why it goes like T to the alpha, but let's say it goes like that. And then what is the velocity at the beginning? That is T alpha minus 1. So you have a process that instead the random walkers inside this material, the electrons, are going, instead of linearly in time, they are going sublinearly. This is sublinear because alpha is less than 1, slower than normal. So this is called, essentially, this is sublinear. Now, we know already that this is transport. What do I mean by transport? We had here an electric field, so you move on average. But let's say if the average field is 0, this is just a dictionary for you. So if the electric field was 0, then of course average X is of course equals 0. There's no possibility to go in one direction or the other. Then we have in some cases, this is just jargon, which I think maybe was mentioned. Let's say you have T to the alpha, and this is called subdiffusion. Subdiffusion because this alpha is less than 1. So it's sub, it means slower than. These two phenomena are actually related. While the first experiment was on transport, there was an electric field. Why was it on transport? Because the easiest thing to measure, if you want, is current, right? Current you measure from Kirchhoff's day, 150 years ago. So it's very easy to measure these currents, relatively speaking. So what we believe today, that if you look at these electrons without an electric field, they will diffuse, and they will diffuse like this, slower than normal, because the mechanism that leads to both these effects are related, and these are trapping events, deep trapping. So now we want to start understanding where does this alpha come from. So the idea that we will develop later the mathematics and all the theory later from the stochastic point of view. First I'll talk about the physics, and then I'll simplify this later on, and then we will look at the math of this. But what do I mean by trapping? So what is going on in a very disordered material? You have this random walker, in this case an electron on a hole, and it sees in the material all kinds of obstacles, it sees all kinds of potential fields. It's very, very complicated. No one can solve it from first principles even today. So the idea is, one idea is like this. The potential, this is called a trap model, and this is also a simplification. You have a particle, there is a thermal bath, let's say with temperature T, and the particle is going to be, let's say, in this trap at the beginning. What is causing this trap? These are all these atoms or these molecules, all the junk inside. Because you have some molecules, they are oriented in some very complicated way. We don't know exactly how to get this trap, but this is a good way to start thinking about the problem. So you see that this is the potential field, V of x. I'm plotting it in one dimension. This is the coordinate x. In addition to this, we also have bias, which I'll talk about later. But forget about the bias. This is just the random energy landscape that the particle is seeing in the potential. This is a very complicated potential. So what do you see here is that the potential itself is random. Usually in physics you are used to, okay, I have a potential, like Coulomb potential or something. But in a real disordered system, you have no clue what the potential is. So we say that the potential field itself is random. It means that the electron will see, let's say, this potential, but maybe another electron that is started somewhere else might see some other potential, like this. So the potential itself is random, and you need to describe its properties. It has, for example, here there is this is the trap. This is the trap. It has some depth. I need to describe how deep are these traps. There is some statistical law saying, okay, all the traps are the same. For example, that would be an ordered system. All the traps are with some distribution. What is this distribution? What is the width or the depth of this trap, how is it fluctuating? That is something you need to put in from the outside to describe the randomness of the potential. You also need, in principle, you can have correlations, that is this depth of this trap related to this trap. So usually what we are going to assume, and many people do this, actually nearly everyone, the depth of this trap and the depth of this trap is non-correlated. Because this is this by the way is a complicated problem. It's not a trivial problem, it's not something you can easily solve when you have this random energy landscape. One reason is, now you say, okay, this particle here is coupled to a thermal heat bus. So what does it do? It most of the time, sits down here, right? But once in a while, because it's interacting with the thermal heat bus, with temperature T, some phonon comes or whatever comes, and then it will go up in energy. It will gain energy from the bath, and then it will go down here, and then it will fluctuate here, and it will sit here, and then maybe it will go back. But let's say there's an electric field. Let's say it always goes in that direction, and then it will go down here. It will stay here, and then it will go up here. Again, that is with a strong electromagnetic field. With a strong electromagnetic field, the energy landscape is actually like that. There's a very bad drawing. This is a bias. This is the constant electromagnetic field that drives it. Is this clear why it goes like this? This is simply, I add to this potential field a constant electromagnetic field times x, that's the potential, with a minus sign, and then you have a potential that is random but goes like that. And then each time the particle is here, it will like to hop here. Okay? But here we understand this complicated model you can simulate, for example, with the Langevin equation. So you have dissipation in this problem, you have fluctuation with the Fokker-Planck equation, and then you have a random potential. But because the potential is random, it's very difficult to solve it, because then even if you solve it for one random field, but then you need to average over the randomness of the field itself. So you can look at things like, for example, what is P, X, and T? P, X, and T, you start here and you have one realization of the disorder, one random potential, one only. But then you can also take this and you can average this, the probability to be at X at time T, you average it with respect to the random field. So, and that is a very complicated procedure. So this additional average, so there is a propagator probability to be at X and time T for one given potential, but then this potential is not special, then you need to average over all the potentials in your ensemble that you create different potentials. You get some average, and then the question is, what is this guy? That is a general problem of diffusion in disordered material. We are just touching this gigantic field. But what we want to do is we want to start thinking from a physical point of view. So here there are energy traps, as I mentioned already. This energy trap, this energy trap, this energy trap, and maybe this guy is the biggest one. This is the depth of the trap in energy. What do we understand? Where the time to escape from here to here, this trap is relatively shallow compared to the time to escape from here to the next label. It's obvious that the deeper the trap is, more time it takes you to escape out and go to your nearest neighbor. Because if you are in a deep trap, the probability of you getting energy activating from the bath is small. Because if I call this delta E, this is site, I'm going to label the sites. This is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, this is 8. So this is delta E8. And this guy here is delta E1. So if delta E8 is much bigger than delta E1, why? Not because 8 is important than 1, it's just because it happens that there is a deep trap here. Then it will take this guy, if it arrives here, to escape much longer than here. And we can even quantify this in very general ways. This is the so-called trap model. And the idea is that the time of escaping from trap number 1 is proportional to E delta E1 divided by temperature. This will be E1. And from trap 8, it's going to be delta E8 over T. And here there's a constant that is not important. And of course, this is general. I mean, it's not only for trap 1 and trap 8, for any one of these traps. This law is very famous. You actually know this law. What is this law? This law is simply Boltzmann factor. What does it say? It says the following. I am in this trap here. I am not moving, and I get into local thermal equilibrium. Then the probability of me to be upstairs here is proportional to the Boltzmann factor, which is delta E over temperature, the thermal temperature. Now, this law, so this is simply Boltzmann. And more generally, Arrhenius. So Arrhenius law is a very famous law that if you take, let's say, a molecule and you put it in a liquid at temperature, and you ask how long will it take the molecule to break, this is the same as asking the question, how long will it take a particle coming from here to go upside here? So this is called the escape problem. So you look at the molecule as there is its relative distance between the two components of the molecule is given by some equilibrium, which is here, and then it fluctuates the size, and then most of the time it's like this, but then once in a while this molecule will receive a lot of thermal energy from the environment, and then it will break, and then the relative coordinate is escaping, and then this will happen, the rate of this escape will be related to this Boltzmann factor. So thousands and thousands of chemical reactions in chemistry departments, but also in physics departments, what they do, they take molecules, they put them in some medium, and they change temperature, and then they look how long until it will break, right? You just measure how long it will take till it break, and the universal law is this Boltzmann or Arrhenius law that the time to escape, the bigger this delta E is divided by T, the longer it takes to break, which is very trivial and obvious. But again, I'm saying that this is kind of the most basic thing in chemical reactions is that you get this Boltzmann factor, and that's why it was discovered by Arrhenius. I think Arrhenius discovered it before Boltzmann. You just measured, you take chemicals, you put them in a system, and you heat it, and you cool it, and you just check how long it will take to particles to break. So it's very standard thing. So this is what I'm trying to say. This is something very standard and basic. The question when you have a disordered system is that this delta E, this thing here, this thing is random. It's a random variable. We call this a random type of randomness quenched random variable. Quenched, what do I mean by quenched? This delta E in the trap model is fixed. It doesn't change in time itself. This, if you come here, you have one delta E. If you come here, there's another delta E, etc. It means that the disorder is not changing. By the way, I assume you had, for example, an Anderson localization, right? Anderson localization is the same problem, but with quantum mechanics. That means that you have a random potential, and what do? You solve the Schrödinger equation with this random potential, and then you want to ask questions like, is the wave function localized? Is the wave function spread like in Bloch theory? Etc., etc. This Anderson problem, people in condensed matter talk about it all the time. It's really beautiful work because you get localization of the wave function. This, in some sense, is a similar problem. You also here have a disordered system, but you are not talking about wave functions. You're actually talking about classical diffusion in a disordered material. But the problems are very much related, only this problem is found in billions of experiments, while Anderson's localization, you need to work extremely hard to find it. It's not that it's not beautiful, it's a beautiful theory, but this is something you find in many high temperature. You don't need to work so hard to find this type of anomalous, and this alpha, it's like became very common. Because actually, what is happening in real system when you have Anderson localization and you solve the Schrödinger equation, but there's no temperature there, right? But in real system, there is a temperature, so they turn into classical, and then you see the classical behavior, which is this one. So this is a problem, and the idea now is, let us look at this Arrhenius law, and there is a transformation now. What do we see here? There is a trapping time, and it's related to a random variable, delta E. So the trapping time, this is random. It's the trapping time in one site. It's proportional to some T0. That we don't care about this T0. This is some number. I mean, what do you mean? I don't care. I don't care because I only care now about this alpha and not about these prefactors. I'm not saying it's totally not important. What is this tau 0? This is roughly, the particle is in here, it hits this wall every tau 0 times, and then it's in thermal equilibrium. So this is the time scales in the inside. Again, there's a lot of work, what is this time scale? And then this is equal to exponential E over T. Here there's a K Boltzmann, but I write K Boltzmann is equal 1. Now this E is random. Now, by the way, short remark. I drew here one energy landscape, and I emphasize that these traps are random, but you can have many other things. This problem is, again, it's gigantic. What do I mean many other things? You can have barriers that are random. You can have many other options. You can do it in 2 dimensions. You can do it in 3 dimensions. There are hundreds of papers on this. I'm just showing you one model because it's complicated enough, but you have to know that there are many, many models in this family of models that people solve. So this is random and this is random, but you see this is a very simple transformation. Again, deep traps, long waiting times. Not so deep traps, short waiting times. That's really trivial. But we can do now something a little bit better. We can look at the probability density function of this random variable tau. That is simply given by the PDF. This is the famous transformation of E. This is the energy, not to be confused with the electric field. This is the energy. And here we have the Jacobian dE d tau. So now what I'm saying is, give me a distribution of these traps, and I'll tell you what is the distribution of these times, assuming that you have this simple activation law. Now, so the bottom line is, what is really important is what is the distribution of the depth of the traps. If all of them are the same, then all the times are the same. What we will get then, we'll get something like a usual random walk. If this distribution, the PDF of the energy of the depth of the trap is this E is positive. If it's a delta function, then the time here, all these traps are the same. This is an ordered system. And then the time here, the time here, the time here, etc., all of them will be exactly the same. There will be no fluctuation due to the disorder. And this is what we call an ordered system. And then you'll have a usual random walk. So what people envisioned, let's take something like this. So here E is bigger than 0 because E is the energy, is the depth of this trap. Minus this is the energy, right? So this law, this is the PDF of E. Is a simple exponential. It means that the depth of these traps is not something really, it's not extraordinary. The P of E is simply decaying, and it's decaying with a typical scale. What is the average energy trap is something that I call TG. TG, it has units of temperature because K Boltzmann is 1. What is TG? Why do I call it TG? Can anyone guess? What is this G? G is glass. So this is why it's called glass. This is sometimes called the glass temperature because of many reasons. This is a glassy system. A glassy systems, you know, this glass that you see here, it's actually like a fluid. It's very amorphous. It's very disordered. It's not. There's no structure. And this typical scale, TG, is a measure of disorder. If TG is big, then the traps are big. And if TG is small, the traps are small. TG is not a property that we calculate here. People did work a lot about this. But TG is specific for the material. I take one disordered material, it has this TG. I take another disordered material, it has that TG. It's not universal. It's some measure of how random these things are. Now I said big TG and small TG. What does it mean big and small TG? TG should be compared to something. To what is it compared? To what? No, TG itself is the disorder. But there are two scales here. There's TG, which is some number which is fixed, which is the energy scale here, how big these traps are. And what is the second energy scale? Temperature itself. So the game here is very simple. If temperature is bigger or smaller than this TG, so there is TG, think about TG. TG is equal 1 if you want. Just simplify because I'm not saying what it is. Then the question is the temperature less or bigger than that number? That will create a kind of phase transition in the dynamics. And phase transition in many properties, in everything. I mean, in ergodicity, in stationarity, in whatever you want. So the big question is T bigger than TG or T less than TG? So if TG is fixed, TG is again a measure of the disorder of the system itself, and then you cool it, you cool the system, you make it lower and lower temperature, then you reach into this phase T less than TG is called the glassy phase, while T bigger than TG is called the normal phase. And this is very simple. Let's say TG is fixed, so you have this random energy landscape, and then you make the temperature lower and lower. Then when the temperature is 0, then when you start here, you're stuck here forever. You cannot go out at all, because the Boltzmann factor, if temperature is 0, is infinite, and the experiments are not done on an infinite amount of time, right? Because you live for a finite amount of time. So at very low temperature, the particle is simply stuck where it started and doesn't do anything. When you change the temperature, you make it larger and larger, then if you look for long enough, it will escape, but it will escape very slowly. So this is going to be the question. t less or equal tg. And let us now see this from these two transformations, which are super simple, because we can now do this. Because this is a, oops. Because after all, I have here the transformation, so I can easily calculate the Jacobian, and I have here the PDF that I assumed of the energy traps. Then I can calculate the PDF of waiting times. This is a simple exercise. So, first of all, tau divided by tau 0 is e exponential over t. But I want to calculate the Jacobian, so I want to know not t as a function of e, but this depth of the trap as a function of e. And again, this is this Arrhenius-Boltzmann thing, so I have here log t over t0 that times temperature, that is e. And then dE over d tau, this is the Jacobian. This is simply tau to minus 1. Because the derivative of log of tau is 1 over tau. On the other hand, I need to just plug in. So what is the PDF of the waiting times? This is the PDF of E. This is the PDF of E, but now I need to plug in, instead of E, I need to plug in this thing. So it's 1 over Tg exponential minus E. So I have T over Tg. This Tg is this Tg log tau over tau 0, and the Jacobian I just now said is tau, this temperature, divided by tau. But you see, what is this? This is exponential of log. This guy I can of course put here on tau over tau 0. So let us define let us now define alpha as T over Tg. You already anticipated that T greater or smaller than Tg will have two different behaviors, and now you see what exactly I mean is what I said at the beginning of the class, that is alpha less or equal 1. So here you see that this is equal to, let us write, forget about the constant here, there's some constant, but what is important here is this tau to the minus 1 plus alpha. The 1 comes from the Jacobian, and this alpha comes from exponential of log, and this minus sign gives you this minus alpha. This is what we are going to assume all along. I'm calling this PDF of waiting time, I'm going to call it psi. So this is the PDF of waiting time. This is proportional to tau minus 1 plus alpha. And then you know that the average time, what is the average time between jumps? Well, you know this already, I hope. This is psi tau times tau d tau, and in principle you need to integrate from 0 to infinity. By the way, here this is for tau greater than 1. But we don't care about the small tau, we care only about the long tau. Why do we care only about the long tau? Of course, this depends on what are the questions we are asking, but essentially we care about the dynamics which is very, very slow on the long trapping times, because we are going to look at it, for example here, Px and T for long t. So you care about these long trapping times. So this is tau greater than 1. This guy then is the following. It's infinity If alpha is less than 1, this is low temperature. Because you know, this power law decay is like -1. I multiply by tau, it's tau to the minus alpha. If I integrate it till infinity, then I get tau to the 1 minus alpha, but alpha is less than 1. This diverges, while here, this guy will be some number. We can calculate this number, but I don't care about it. It's finite. This is finite, and this is a high temperature. Now you can say, how do you know that this is this law? Because you see, essentially what I said is that if the distribution of the energy traps is exponential, then you get power law waiting times for this process, and then you have the diverging of the mean. Then many interesting things will happen. You can say, wait, why is this correct? So there are many answers to this. In some cases, it's not correct. In other cases, you can prove it in experiment, and in other cases, you can prove it from theory, but from some certain assumptions. Let us discuss only about phenomenological approach. Phenomenological says, okay, you assume something, let us check if this is correct. How will you check this? It's easy. It was checked roughly when Scher and Montrol did their theory. The guys in Xerox we said in Xerox they simply measure, right? Measure, well, maybe it's not so simple, but and this is the current as a function of time, and here I have T alpha minus 1. Okay, so then you do this, and here is T minus alpha minus 1. You do this in 1 temperature. Good. And then let's say you do it when this is anomalous. This is important, not when it's normal. So you go to low temperatures, and then let's say alpha is always less than 1. And then you just plot alpha versus T over some fitting constant, T over Tg. And then you'll see there's a straight line. And then you say, okay, alpha is T over Tg. Alpha, though, less than 1. So all I'm saying here is something very simple. This prediction is not the whole story. It's just the beginning of the story, but you can simply check it in laboratory. By changing temperature, you can get this alpha T over Tg. And actually, the truth is,
how do they know what is Tg?
They don't, but they fit it, because they measure alpha. They don't know it. But they don't know it, but they see it's linear in temperature, and then there is some slope for this curve, and that's what they call Tg, okay? This is what I said, a phenomenological theory, but due to this is real life. The material itself is so complicated, you don't have a first principle theory. At this stage, this is 1974, you say, okay, this alpha is T over Tg, and then you see that this law is not universal. Some materials, you see this. Some other materials, you don't see this. I'm not claiming this is all the story. It's some experiments are like that, some experiments are not like that. What does it mean it's sometimes like this and sometimes like that? This is something really good, because I showed you one model, but there are many models that bring this. It's not one short story that you explain and that's it. There are many other models that give you other predictions on alpha, which is not related to temperature at all. So this is a huge industry. If you think it's something you fit, it's work in progress till today in some sense. So it's not clean physics, it's disordered material. Disordered material are complicated. And there are many phenomena and many interesting things, and we're not studying all of them, because that will take you all your life. There are many more experiments like this. So I'll just mention a few. So, for example, roughly I think 2004, there's a nice experiment that I like by a guy called White. He's from Harvard. He did the following experiment. This is more or less a single molecule experiment. In the cell, there is some network that I'm not an expert on, and it's called an actin network. It's very important for the maintenance of the structure of the cell. It's in every cell. I mean, if something is defected with this network, you're dead, or you're sleeping like Leo. Anyways, people are interested in the dynamics of this mesh. So again, it's in temperature T, and there are some viscoelasticity. That means people shear it, and they tear it. And he did an experiment where you take a sphere and you follow this trajectory of this particle. And this particle will get stuck, and then it will jump here, and then it will jump here, and then it will jump here. And it gets stuck between, so think about this as your noodle soup or spaghetti soup, and you have some small thing. This thing is roughly 1 micron or smaller. The beautiful thing about his experiment is he could change the radius of this thing. So he had a knob on the radius of this sphere. It started from 1 micron, but you can go in a range, I don't remember, from let's say 0.1 micron to 2 micron. He simply prepares different spheres and he throws them inside, and then he sees what happens. I mean, it's not so simple, but he was capable of doing this. So when you have a very, now importantly in this system, this mesh, that is the distance between your spaghetti noodles in your soup, the typical size of these cages. So here you have cages. And you see in spirit is like what I told you before. But before I said it was energy traps. So the trap was in energy space. Here there is also some traps, which is what you are surrounding this bead. A very complicated motion. And maybe this thing has to open, and this is an activation process or whatever. It will take some time till the particle can hop here. So if you have a very small particle, so this is like small, of order of the size, let's say, of the water molecules, or much smaller than this mesh size, 10 to the minus 1/10 of a micron. This is, let's say, 1 micron, this is 1/10. So everything here is in water. What happens to this very small guy? It doesn't see this mesh. It just diffuses. There's a random walk inside. He sees nothing. And then you can measure the MSD. This is the MSD. There's no drift now. There's nothing. And this thing, for the small particle, is going like T. This is for the small particle. What happens if you have a gigantic particle? It's also obvious. X squared goes like T to the 0. You look at the experiment, of course, for some finite time. I mean, the experimentalists do this experiment for 1 hour, let's say. You put in something gigantic into this actin network. It's simply trapped. It cannot move because all of these actins are around it and it doesn't move. So if you have something bigger. But if you put something which is roughly 1 micron, this goes like T to the alpha, and alpha less than 1. This alpha depends on this radius. This is just what he sees. So it goes from here to here, then he can change the size, and then as a function of the radius. And then, now there is a matter of definition. What do I exactly mean by this alpha? There are actually 2 alphas. One of them is x squared, let's say, goes like T to the alpha. We will show that this is the case if you have this type of waiting time. One of them is psi of tau, tau minus 1 plus alpha, here alpha less than 1. Okay, so we're going to show this later, but I'm just telling you what you see. So as long as alpha is less than 1, that means you are in the limit of size micron and lower, and you are not doing normal diffusion. There is a phase transition, so to say. So when R is big, so maybe you need to plot it as 1 over R, then it goes something like, and then of course there's some change in the dynamics. So when R is very big, alpha is practically 0. And then when R, 1 over R, this is like 1 over micron, which is the size of this mesh, this alpha is roughly like this. But now he can do something that Sharon Montrol and these old experiments cannot do. You can look at this trajectory because he's using a single molecule technique. You see, when Sharon Montrol were talking about these things, they were talking about a huge number of electrons, but you don't see the electrons. You don't know what's going on. You don't know if there are waiting times. You don't know, I mean, indirectly you know that there are waiting times, but you don't see the waiting times, right? Here you can see the waiting times because you can say, okay, I have here a mesh. This particle decays here, stays here. Then I can hop here. Then I'll see how long it stays here. And then I can discretize space. And then I can look at the probability density function of the waiting times themselves directly from the trajectories. Again, because I have single trajectories. So what they do in this experiment is the following. They create kind of a mesh, which is the mesh. And then they say, okay, the particle is here. Then it jumps here. And then it will go maybe here. This is already a 2-dimensional random walk or 3-dimensional random walk. And then you plot psi of tau versus tau. And you see that sometimes the particle, maybe you see here, it will get here, it will be trapped for a very long time. Sometimes it's here. And then when you plot it on a log-log scale, log psi, log tau, you simply can measure this t to the minus 1 plus alpha. And then you go back, you measure this alpha, and I claim this alpha and this alpha are the same. And this is the theory of continuous time random walk that, again, was developed by Sharon Montrol. So the main message is that there is a big difference when you do experiments on an ensemble of electrons, where many theories, you can put forward many theories explaining, you know, this x squared t to the alpha, many reasons. But when you see the trajectories one after the other, and you see exactly what's going on, then you can come roughly 30 years after Sharon Montrol, and you can show, oh, in this experiment, it's really parallel waiting times. And you can tune in this experiment, it's in Sharon Montrol experiment, this was temperature. Here, this is related to size, very different mechanisms of trapping. But the nice thing in both experiments, you can, in principle at least, you can control this alpha, changing the size of the bead here with whites or changing the temperature in the older experiments. And then if you can change it, then you can go from one dynamics, which is subdiffusion or anomalous diffusion, to normal diffusion. You can go from a situation where the mean exists and it's finite, which is normal diffusion, to a case where the mean of the waiting time is infinite. This was found in many other experiments, but just by observations, and it's found in fields like turbulence. So there's a very nice experiment, for example, by Sweeney. It's a guy from Texas. So Sweeney took two rotators. These are two cylinders, and he rotates them very quickly, one in this direction, the other in this direction. and in between there is fluid, there's some water. He wanted to, this is a very simplified model of flow, let's say in the ocean, where the rotation is related to the rotation of Earth. He simply wanted to create some vortices. So here I have vortices. In his experiment, when you turn it fast enough, you create vortices. In his experiment, he had 6. But this is not so important. This is just turbulence. This is like hydrodynamics. For us, I'm not going, this is not a course on continuum mechanics, but he creates it. The point here is that in this example, this is why I'm telling you about this, there is no temperature, there is no heat bath, it's all, the flow lines here, this symbolize velocities. So if the particle would be here, you solve the Navier-Stokes equation, then it will circulate here, but then there are also other trajectories like that. The point is it's totally deterministic to first approximation. And my point is that all what I'm saying here you can get out of nonlinear dynamics. It's again a field by itself. So in chaos theory there are a huge number of works which give this psi of tau decaying like power law, and then it's not related at all to temperature or to size, but to some parameters of the flow field. So what I want to say here is that chaos theory and turbulence also, there's a lot of these things. But what he did in this particular experiment, he just follows a tracer particle in this flow, and then when it goes into vortex, it's very complicated motion, and he looks at how long it stays in a vortex, and this is again a power law. There it's more complicated because you also have power laws between vortices. The bottom line is very simple. There are many different types of experiments that show these power laws, and we showed it from a very simple model, but it's only the tip of the iceberg in reality. So this was a physical introduction. My whole point was like this. There is psi of tau. We can see it in experiments that decays like a power law. This describes the time between jumps. So we'll go now for a break, and after the break we will say what is the model, how do you couple the trapping times and the movement, the motion itself. Because up to now I just described you the time, but then how do you jump left and right? That would be actually the easy part, because the jumping left and right will be exactly like the usual random walk. So the idea is you wait and then you jump, you wait and then you jump, you wait and then you jump. And the new element compared to the old random walks is that these waiting times are given by these power laws. And then we ask questions like, what is the average X? What is this average MSD? What is the propagator? This is the stochastic element of this theory. Here I just gave the motivation, so please go for a 10 minutes break. But before that, please give me the exercises. And I'll also give you the next exercise that you need to hand in next week. So the next exercise, I'm writing down here questions. Is Q1, Q3, Q4, Q6, 3.4, 3.5, 3.6, and 3.1 till, wow, I think this is a mistake, 3.3 or 3.2, I think 3.3. It's a bit of a mess because on my web page you'll see one of the files is more details. So these questions at least should come from the file called more details, but in general this comes from the file called fractal renewal theory. And this is chapter 3. By the way, by solving this fractal renewal theory, we did it already a few weeks ago in the class, but this is actually the basics that we will use after the 10 minutes break to solve the CTRW. So fractal renewal theory, these are the waiting times with these power laws that previously I just introduced ad hoc. Now you understand where it comes from a little bit more. But this and CTRW go hand in hand. So if you don't understand this, then it will be difficult. The next lesson will be even more difficult because we rely on this a lot. So unfortunately, last week you had a break. So you're a bit lagging behind me, but I'm sure you're young, so you'll pick up next week. But hand this in next week, please. So we are now going to define the mathematical model called the continuous time random walk. The main equation here is going to be an equation called the Montroll-Rice equation. And we want to know what is the propagator, the probability to be at r at time t for this type of random walk. For that, we first need to describe the model. So in this model, we have two descriptions. One of them is the PDF of jump lengths. And I'm going to call it f of x, f of delta x. This is the microscopical jump. And if you want to think about something, it's going to be, for example, a Gaussian. Or it could be, if you do it on a lattice, this is on +1 and this is on -1. So this is with the two delta functions. Then you have a distribution of jump lengths. It's drawn from this distribution. What is important about this thing is that its moments eventually are going to be finite. We're not talking about Levy flights or things, something exotic where this guy has power laws. This will be the normal part of the model. So in this model, we have IID jumps. We have jump 1, we have jump 2, and we have jump n. So in this process, we are going to say you have a jump length, you draw it from this PDF, you get some number, then you draw it again from this one, and again, and they are independent of each other. Because they are independent of each other and they are identically distributed, that is this IID, it's enough to define this function f of x, whatever it is, and then you define the jump lengths. However, here, n, unlike usual random walk, this n by itself is going to be random because the number of jumps is going to be random. So in addition to that, we have also the PDF of waiting times. Sometimes they are called sojourn times, sometimes they are called trapping times. I'm going to call them waiting times now. Jump events. In this second PDF, this is normalized also. This one is normalized. The integral over tau gives you 1. These two distributions together define the model. You have again IID random variables. They're both independent of these xi's, but they're also independent of one another. And then you have tau 1, tau 2, tau 3. And these describe the trapping times. Of course, another important parameter is t. T is the measurement time. So these are also independent identically distributed random variables. So this means that the time process is a renewal process. Now, the model itself was invented already in 1965, 10 years before Sharon Montroll. And it was invented by two gentlemen. One of them was called Weiss, and the second one was called Montroll, the same Montroll, of course. At the beginning, they were thinking, what is this? What we should use psi of tau? They were analyzing random walks on lattices, very standard condensed matter solid state physics. So they said, okay, psi of tau, most reasonable thing to assume is that maybe it's exponential distributed. Tau is, this psi of tau is an exponential. So 1965, maybe you add something like this, or something slightly more complicated, but the mean is finite. This is 1965. This is like the old theory. Everything is old, also 75 is old for you, but never mind. So this is Montreal-Weiss. Then you have psi of tau, much coming later, that decays like a power law. This was following the experiments, so don't think that theoreticians are so clever. There were experiments, then people were thinking, wow, how can I explain it? And then they said, okay, it's like this Montreal-Weiss thing with exponential, but now we'll switch the exponential to something with power laws. Because going from here to here is a big, big step. Because it modifies the Kirchhoff's law, and modifies all the picture of transport. So here this I'm writing proportional to. Here is alpha, let's say, between 0 and 1. And then here, this is Montreal, actually Cher Montreal. I think 1974 or 5, something like that. So in this case, we have this power law. This is log psi, log tau. This would be a straight line with the power law, while these guys, these waiting times are very simple. They are simply exponential. You plot it on a log linear, or you see exponential waiting times. So how do the trajectories look like? So before doing that, so we start the process at time t0, and then you draw tau 1 from this waiting time, then you have tau 2, then you have tau 3, and if it's a power law, then suddenly you'll see some very big junk with nothing. This is tau 4, and then you draw tau 5, but your measurement time is here, t. So tau 5 is already after. So here in this case, we have jump number 1. This is, you first wait and then you jump. You wait and then you jump. So this is jump 1, this is jump 2, this is jump 3, this is jump 4. So here the number of jumps in this realization, n is 4. So of course, depending what are the waiting times in the process, because t is finite, the number n fluctuates. But this is exactly what I already taught you, and this is your homework on fractal renewal theory, how many jumps you have, what is the average jump, what are the fluctuation number of jumps. This is all well known. What happens in this model is that each time you wait, and then here, here, and here, you generate a jump in space. You take f of x, and then you jump left, right, with some size. Each time, after you waited, you jump. Wait, jump, wait, jump, wait, jump, wait, jump, etc., etc., etc. That is the model. Okay? So the trajectory in space now, when I add the jumps, let's say I do it on a one-dimensional lattice. And I have probability half to jump left and probability half to jump right. So let's say, for example, on a lattice, 1D lattice. That just means that f of x is a delta function. You can jump to the nearest neighbors, although only divided by 2 for normalization. So I'm here, I wait, I jump here, I wait, I jump here, I wait, I jump here, I wait. And each time I draw this from waiting time distribution. So then the trajectory looks like this. I start on site in space 0, and I can be only on the integer, so -1, 1, 2, this is space 3. So I wait, then I immediately jump. The jump time is 0. Then I wait, then I come back, then I wait, then I go here, and then I wait, and then this is my trajectory, and then I stop this process at time t. So when you stop the process, you are trapped somewhere in space, like these the physical traps. You are somewhere in space, and then at time t, in this example, I'm on position minus, this is -2. Okay, so here I have, this is tau 1, this is time. This is tau 2, and these are realizations of the jumps taken from this distribution of fx. Here I'm not saying how I draw this, it doesn't matter, this is just the trajectory. Okay, this is tau 3, tau 4, and this, the number of jumps here was 4. 1, 2, 3, 4, 5, 5. Okay, this is the model. So now we want to find out what is the propagator. What is, let's do it in d dimensions. We cannot solve this problem exactly for every time t unless we choose very special waiting time distributions and very special jump lengths. For example, if you assume that the waiting time PDF is exponential, this is a Poisson process, and the jump length is Gaussian, we can solve it exactly for every time t. But in general, we cannot solve it exactly. And this is not surprising because even the simplest random walk, we cannot solve exactly, right? But we know from random walk theory that what is the general idea? Don't work in space-time, work in Fourier space and Laplace space. So we're going to work in Fourier-Laplace space, because then everything is going to be convolutions, and we can solve it exactly in Fourier-Laplace space. So what is the position of the particle at time t? This is a stochastic variable. This is the final position, like here. Well, it is some delta r in general. I is an index of the jump length. I equal 1 till the number of jumps n. This I just made you maybe confused. What is this delta r? This is the same as this x.
But n is also stochastic.
Absolutely, yes, that's exactly the point. In one dimension, I'll call this x. It should be xi. But here I want to write it like this. So in general, I have f of delta r, a vector. So it's f of delta x, f of delta y, f of delta z. It's a jump in with a vector now. Okay? But in one dimension, it will be just f of delta x. So as you correctly said, this n is random. If n would be fixed, then this would be a usual random walk. So it's a standard random walk from my point of view when n is fixed. We know everything on standard random walks, or at least Montrol and Weiss did. So now the only thing they need to treat here is that this n is random. So the first formal observation is we want to know what is the probability to find the particle on R at some time t. That is equal, based on the assumptions of these renewal assumptions, the sum over n from 0 to infinity, which means that in some experiments, your measurement time t is something finite. In some experiments, the number of jumps is 0. Others it's 2, in others it's 3, etc. You have many options. And this is equal to, let's call this Q Tn P R given n. So this QTN, this guy, is the probability to make n jumps. This guy is related to this psi of tau. Actually, we already thought about this, but I'm going to remind you. So these are the distribution of the number of sums. It's a probability. So the sum, if this would be 1, the sum over QTN is 1, because you have some probability to have 0 jumps, some probability to have 1 jump, 2 jumps, etc. And the waiting times determine this function. This, on the other hand, this is the probability of being on R given that you did exactly n jumps. This is the probability density but of being on R given that you made n jumps. This PDF is related to this f of x or f of delta r in general. But this part, this is just the usual random walk, because in the usual random walk you had exactly n jumps. So this part is the usual discrete time random walk. What do I mean by discrete time random walk? In the usual random walk you have n jumps, jump at time tau equal 1, tau equal 2, tau equal 3. The number of jumps is fixed. That's the usual random walk. And this is what we already studied, so we know everything about this, how to relate this. It's very easy. In principle, in Fourier space. So now I need to remind you. So this is now going to be a reminder. But our goal is to find pk and which Laplace variable I'm going to use, s. This is, again, we know that it's always good to work in Fourier Laplace space, at least at the beginning, with this type of random walks. So this is simply, by definition, the integral from minus infinity to infinity. Well, you have, in principle, you have n-dimensional integral. So I'm not going to write it n-dimensional, but I'm going to write it as dv. This is a multiple integral. For example, if you're working in 3 dimensions, it's dx, dy, dz, integral from minus infinity to infinity. This is a Fourier transform in 3 dimensions, and this contains all the volume of space. And here I have e, I, k, r minus s, t, and here I have another integral from 0 to infinity dt of p, r, and t. So what is this thing? It's the Fourier Laplace transform. It's, you take r, you go to k. You take t, you go to s. So all along we'll have t goes with s, and space goes with k. So what is, we know, we showed already that q s, now I'm working in Laplace, so I'll add this hat, of n. Does anyone remember? Or AI? This comes from the renewal assumption. It's a complicated equation. I'm not saying this is something intuitive from start, but essentially it says the following, that if the probability to have n steps is given by psi s to the power n, and you have this factor, this is this related to the probability of not moving at all. And this to the power n at least is very intuitive, at least for me, because I saw it a million times. Because what is a pk? This is Fourier space n. this maybe you remember, but this is simply f of k to power n. So this guy and this guy are similar. And this guy is something you should remember. I hope you remember it. It's very simple. But I remind you, but it was in the class already. It was in the homework. This is the usual random walk, that the position is the sum. So this is something simply because Eik dot r, which is the Fourier transform of the position, given that you have exactly n steps, is simply Eik delta ri, r1, Eik delta r2, blah, 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 Eik delta rn, the nth jump. And then you say each one of them are independent of each other. So this, and they are also identically distributed. These are the jump sizes. So this, as you hopefully recall, is Eik delta r to power n. And this is what I called f of k. If you want a tilde here, I'm not against that. To the power n. So what is f of k to the power f of k? F of k is simply the Fourier transform of the microscopical jump. You have this microscopical jump, and then you take the Fourier transform. Delta r, f of delta r, d delta r. It's a volume integral. If k is a vector in one dimension, it's simple one-dimensional integral. Now, for this continuous time random walk, then what do we need to do? We have to just take this information that was already on the class and just add them together and then sum. So it's fairly simple to find the Fourier Laplace transform. So we said P R T, I deleted it, was the sum over n equals 0 to infinity, Q T n P R given n, but n is fixed. Now, what did we say up to now? This guy, I know the Laplace transform. This guy, I know the Fourier transform. Notice that here there's no t. Here there's no r. So if I know the Laplace transform of this, and I know the Fourier transform, I know the double Fourier Laplace transform of this object. This is what I'm looking for. S was the Laplace variable. And that is equal Qn. First, you need to sum now. Okay, that will be not so difficult. The weighted time PDF in Laplace space. This psi of S is, of course, the Laplace transform psi of tau. Here I'm just copying the equation that was just over there somewhere. And here I have f of k to the power n. But now I see that this is a simple series, because this guy I can take outside of the sum. They have psi of s f of k to the power n, and I need to sum from n equals 0 to infinity. And psi of s, if you think about it for a second, for any finite s is less than 1, and f of k for any finite k is less than 1, because these are Fourier transforms and these are normalized functions. So it's very easy to sum the series under the condition that psi times f in Fourier Laplace space is always less than 1. Then I can sum up the series, and then I get a famous, in the random walk community at least, community equation, which is this equation, 1 minus f of k psi of s so this is this infinite series. The sum over x to the power n gives you 1 minus the summand. This equation is called the Montrol-Weiss equation. Now, in principle, if you are mathematicians, you are done if you just care about any time. Because you give me what is your f, you give me what is your psi, then you go to some computer and you invert it. You invert it from k to r, from s to t. So, but this is in 3 dimensions. You have a 3-dimensional inverse Fourier transform, a 1-dimensional Laplace transform, that's 4 dimensions. So in general, this is not an easy task, but in principle, you can do this if you want, at least for some choices of, if you know these f of k's and f psi of s. But this is, of course, can be done, but it's not really insightful. So what we want to study now is, let's start with the simplest thing to study. What are the moments of the random walker? Where is the particle on average at time t? Maybe even before that, the first sanity check to do is the first thing you always do with these type of things, the easiest thing to check is that check normalization. How do you check normalization? You take k equals 0. So what do you expect? You expect p k equals 0 of s. So this is the, simply, let's write it explicitly, ik r p r t e minus st. You have integral over volume and over time, dv dt, but we take k equals 0. So we have an integral over volume of p rt, that is equal 1. Then you have the integral of e to the minus st times 1 dt, that is 1 over s. So if you invert this to real time, that is simply 1. So the inversion of this 1 over s comes from the fact that I'm still in a plus space. And indeed, if f of k, as it should, k equals 0 is equal 1, that means that the distribution of the jump sizes is normalized, as it should be. Then you get p from the Montrol-Weiss equation s. This is 1 minus psi s over s. This f of 0 is 1. You have here 1 minus psi s. This is 1 over s. So this is just to check that they didn't make a mistake on the way. I mean, this is how it should be. This is independent of what is f of k. It can be even with some power laws. What is psi of s? It doesn't matter. You are always normalized. Let us do something more insightful. And okay, we check the normalization. The next easiest thing to do would be the average. Let's calculate the average position of the random walker. And remember, in the experiments of Scher and Montrol, this was the derivative of this was the current that they were measuring. Right? So the first moment is already insightful. So let us also simplify things. So let us first of all walk in dimension 1. And we want to calculate x average. That's just the mean. So to get mean, we need to, first of all, of some f delta delta x, which is not symmetric around 0, because if this function is symmetric, like a Gaussian around 0, then the average is 0 from symmetry, right? Which means that you need some PDF. This is x, this is 0. This is the, again, this is the displacement. You need some, let's say, Gaussian with a mean. Okay, let's call it delta x because it's with a mean which is finite. In the physics, what is this delta x? This delta x is proportional to what? To the electric field, to the what is pushing the particle in one direction. But now we just say there is a finite size of the jump. Why we must have a finite average size of each microscopical jump? Because then each step you move more to one side, more to one side. Sometimes you can move backwards, but on average you move to the right. And then this delta x, we're going to assume that this delta x average is something. And actually the mean x is going to depend only on the delta x and not on the full shape of the distribution, which is actually very obvious. So let us calculate this, and assuming that you have this mean, this is not 0. So how do we calculate this? So okay, in general, if I have I kr, then from here, you know that the mean r, in general, not in one dimension, is equal d over dk. Okay, let's do it in one dimension. Let's be consistent. So the average position is simply, I take the derivative with respect to k, because this is a series, so it's 1 plus ikx plus k squared x squared. I take the derivative with respect to k and then take k to 0. Then I get eikx. And then I need to add here a minus I here. So, but what is this eikx average? This is just the Fourier transform of the position. So the average of x, this is on k equals 0. Is minus I d over dk 1 minus psi of s 1 minus f of k psi s. And here I need to take k equals 0. What is this object? This is the Laplace transform of the average position. This depends on s. So after I find this, I need to go back from s to time. So I'm first just finding the Laplace transform of the position. Here, eventually, I want to find the position in real space, in real time, and for long times. T has to be large, otherwise it's non-universal. And what I did here is just plug in the Montrose-Weiss equation. Bless you. Okay, so I only need to take the Montrose-Weiss equation and take the derivative with respect to k. So that is kind of easy. So the average x in S space is given by minus I 1 minus psi of s divided by s. Here I get 1 minus f of k psi of s squared, because I'm taking the derivative here. Then I need to take the internal derivative. So I have here d over dk f of k. And here I have from downstairs, I have psi of s. Now I get a minus sign because this is downstairs. I get one minus sign, but then I get a second minus from here. So I get this expression minus times minus is equal plus. And all this I need to take k equals 0. But then I realize what is minus I dbk f of k equals 0. This is, of course, just the size of the microscopical jump. I hope you see this, but it's the same as here. F of k is the, you can write it in case you are not experts, which you are not. Here I'm writing what is f of k explicitly. When I take the derivative, I'm going to put downstairs ix multiplied by minus I, that gives you plus x, and then this guy is equal to integral x dx, which is, okay, this is what I call the size of the jump, microscopical size. On average, each step you move this amount. So what do I get for the position of the particle after many jumps? In principle, many jumps, but in S space. This f of k, this goes, what is this f of k? K equals 0, this is normalization, this goes to 1. So I get like this, I get delta x average. I get 1 minus psi of S. 1 minus psi of S squared, and here I have S. So I found an exact expression, exact in the following sense. Doesn't matter what is the waiting time PDF. It can be exponential, it can be whatever you want. The average position is given by the microscopical size of the individual jump times S 1 minus psi, the Laplace transform of S. And I made a mistake. You didn't correct me. Because of this psi of S here, here I have another psi of S. So it's even uglier than you can imagine. This psi of S, this psi of S, this. Okay, but what is all this junk? What should it be? Can anyone guess what it should be? What is this? I explained what is the delta x. What is all the rest? Average of what? The average of you are very close, but no. This is the average number of jumps. It's simply the average number of jumps in S space. So all this guy is the average number of jumps in the interval 0 to time t, but it's not in time t, it's in Laplace space. And this is obvious from the start, because we didn't need all this math to understand this, actually. This is just a sanity check. But let us see why this is obvious, and then even I'll prove it to you. Because what am I saying? I'm saying, you know, the average position of the particle R is the sum over delta Ri, I equal 1 till n. This is, in one dimension, this delta R is delta x. So let us do it in one dimension. I'm just saying that the position of the particle is the sum of these delta xi's So I'm just saying that the average position in time now is the average of n times delta x. This is what this equation says in a slightly more complicated way. This average of n, of course, depends on what is psi, what is the waiting time PDF. To show this, this was actually, I think I showed it to you already, but let's do it again. What is the average number of jumps S? This is simply the sum n going from 0 to infinity, n times the probability to make, I'm now in Laplace space, so this is S, probability to make n jumps. And that is nothing but the sum n equals 0 to infinity, n 1 minus psi s divided by s, psi s to the power n. This was just the probability to make exactly n jumps. So here we get 1 minus psi s. So here we have no jumps in space, only the waiting times, right? So I just got this factor I can take out, and then I have this sum, which I can write as psi of s d psi sum psi s to the power n. Because when I take the derivative with respect to psi of psi to the power n, I get this n downstairs, but then I get n minus 1, and that's why I need to multiply by this psi of s. And this psi of s is essentially the same as this psi of s that you have here. Because this is equal to 1 minus psi s divided by s, psi s. This is from 0 to infinity. Then I take the derivative. This is 1 minus psi s squared. So this is the usual geometric series. I sum it. Then I take the derivative. I get this. And then I get this cancels. Then I get this is equal s 1 minus psi s psi s, which is this. Now we want to, okay, well, now we can just take the fractal renewal theory that we studied and plug it in there, because whatever n is as a function of time, we are done. So we know from fractal renewal theory that if we want to measure large t, this corresponds to small s. This is fractal renewal theory. So in particular, we know how psi of s can be expanded at small s. And what is my notation? Okay, sum minus a s to the power alpha. Let's say here alpha is between 0 and 1. This corresponds, this is the Laplace space, to psi of t that decays like tau minus 1 plus alpha. This is, I remind you, this is like the Tauberian theory. We studied this a few weeks back. There is a Greek factor here related to this a. This a has units of time to the power alpha. This is a number. And the one is simply normalization. Because when s is equal 0, then this PDF is normalized, this is 1, and this is the leading order expansion. I want to remind you that I have here s to the alpha. This is a non-analytical expansion. for normal PDFs in the sense that the average is existing. So let's say you have let's call this case 1. The normal case, the standard case, let's say psi of tau is e to the minus tau, which is exponential with the rate 1. Then psi of s, the Laplace transform is 1 plus s. This is the Laplace transform of this thing. And then this has an expansion 1 minus s. So you see here it's s to the alpha because of the power law. This one here, or more generally, it's 1 minus the average time between jumps times s for small s. So this is all a reminder. So all I'm saying here, because alpha is less than 1, the average doesn't exist. This A replaces in some sense the average. It describes the far tail, how this describes, but the most important parameter here is alpha, which is between 0 and 1. So in this case, what do we get? So we have this thing. So let's look at it. Let's look at case 2, for example. This again, it's a reminder. Case 2, which is the normal case. So I need to look at the average number of jumps in S space, and I look for small s. Then I just plug it in here. So 1 minus psi s. What is 1 minus psi s? It's tau times s. Upstairs I have psi s. But what is psi s in this limit? It's 1. There are corrections, but I don't care about the corrections. I'm looking at small s because I'm interested in large times. I want x average at large times. So here I have times squared. This comes from this s here, times delta x average. So what is the mean position? I need to take the inverse Fourier transform of 1 over s to the power 2. That is very easy. That is t. 1 over s to the power 2. When you invert it, you get linear in time. And then what do you get? A very simple and obvious expression, delta x t divided by the average of time. This is what we call normal behavior. The number of jumps in the long time limit is simply the time divided by the average time between jumps. This is the number of jumps. Each jump, you make the size of delta x. Then your average position in the long time limit is the size of the jump average times the number of jumps average. And then if I want to calculate the current, usual Kirchhoff, Ohm's law, whatever, then you get something like this is proportional to a velocity, and then this is equal to delta x over tau. And then the current is a constant, and delta x is proportional to the field, and then you get Ohm's law. But the more interesting case is case 2. So in case 2, what I need to do is, I remind you, is 1 minus psi s. But now, instead of 1 minus s tau, that give you this average tau, you get something else. So in Laplace space, so you get 1 minus psi s. This is equal to a s to the power alpha. Again, s to 0 corresponding to long times. And then the average of n in Laplace space goes to, again, this psi of s goes to 0, gives you 1. So it's not important. And then you have a s alpha plus 1. So before I had alpha equal 1, so I had 1 over s to the power 2. That gave me this linear in time t behavior, and now what do I get? I get that the average position of the particle is equal to, when I do the inverse, I need to do the inverse Laplace transform. So when I do the inverse Laplace transform, I get, it's easy to see from units, it's times ds. So from units point of view, I have ds, cancels this 1, I have s to the power alpha, that gives you, obviously, t to the power alpha. Again, alpha is less than 1, so it's slower. But then when I do the inverse Laplace transform, I also get the gamma function. And then you get gamma 1 plus alpha. And here I have delta x average. So it simply means that because you have these big waiting times, very slow processes, on average, the number of jumps is t to the alpha. And that's why your average position is going slower than normal. In particular, if I again use that the current that I measure in the Sherman-Troll experiments is proportional to the average x dt, I get the mentioned t alpha minus 1. Remember, this was the initial slope. Eventually, there's another slope, but that is related to something totally different. That was related to how fast you reach the boundary. That's a first passage time problem. So in the Sherman-Troll experiment, the ISM, you had this alpha minus 1, and then you had another one, minus alpha minus 1. But if you make the system size bigger and bigger, this guy goes further and further. We are just dealing now with only with this part. And again, alpha is from a more microscopical model. In some cases, alpha is the temperature over Tg, so you can control it and you can see all this stuff, as I mentioned in the previous class. Now, all this is valid when delta x is not 0, when you have a field and you are pushing your particle in one direction. But many experiments, there's no external field. They just do diffusion. Like the White's type of experiment. He had this polymer network, he didn't apply an external field. He could, I wish he would, but he didn't. So there's only diffusion, there's no bias, there's no driving force. And then, what do you calculate? Well, after the first moment comes the second moment, right? So we want to calculate x average. And how do you do that? Essentially, the technique is very similar to what we did, but it's slightly more complicated because this is the second moment and previously we had the first moment. So the more you go higher in the moments, it's a bit more work, but it's not the end of the world. You can do it. Maybe we will even do the fourth moment if we are lucky enough. So what do we need to do? We need to take, we have P, K, S. We have it from the Montrol-Weiss equation. Double of Laplace transform, Fourier transform. In principle, this is a vector, but let's write it in one dimension. And then, what is the second moment? You need to take the second derivative with respect to k. And then take k to 0. It all comes, again, I'm mentioning it a few times already. This is because pk of s is the Fourier transform of k. Then I take exponential ikx, I expand it to second term. Gives you k squared x squared divided by 2. Then when I take the derivative 2 times, the 2 will cancel with the 2 downstairs. And then you get this equation, which is well known and understood from Fourier transforms. Now what I need to do is I need to plug in the Montrol-Weiss equation and do this. This is not so nice, but it's possible. So you see, you take the first derivative, this is, we already did, and then you take another derivative, then you take k to 0, and you cramp up this machinery. I will not do all the steps here, and just write down what is the solution in Laplace space. And then we will hand wave. So this is the Laplace transform. This is equal to the following. The average number of jumps in S space times delta x squared average. What is this delta x squared average? This is the size of the jump squared average. So this is the microscopical jump, but you have the second moment of it. Plus n minus 1. This is again in S space times delta x, the first moment. Of course, this guy is related to the waiting time PDF, to psi. This guy is also related to psi. And this guy is the second moment of the jump length, and this is the first moment of the jump length. So when delta x is equal to 0, we get something very simple. If this is equal to 0, no bias, no external fields, then we get something that we can easily understand. First of all, in this case, the mean is equal to 0, of course. And the second moment, which is the diffusion in Laplace space, is n of s delta x squared. And this is, if you think about it a little bit, it's an obvious equation, because what is the average position of the particle? You have a sum over n, this sum of these jumps. This is the random. This is a random variable, depending on the sum when n is itself random. So what is this? The second moment? It's the sum over n, delta xi, sum over, let's call it delta xj, and average. We need to average both of n, both of the size of the jump over everything. But notice that delta xi and delta xj, if there's no bias, these two guys are, each one of them individually is 0. So what do I get here? I get here n average times delta x squared. Again, if delta x average is 0. Because you see, I multiply delta x 20 with delta x 30, they are not correlated. On average, they are 0. Because the mean is 0, and they are independent. And then I have the terms which are identical, delta x1, delta x1, delta x20, delta x20. And how many I have? N of them. So then I have the now average n times delta x. But this average n we already calculated, right? This average n was just now on the blackboard. So in this case, we get the MSD is the size of the jump squared, average, times t to the alpha, a gamma 1 plus alpha. Again, this is only for long times. If the bias exists, you also have this guy. This guy is related to psi. But before that it's related to psi, let's see why you have nn minus 1. Roughly speaking, you see here I have these summations. I excluded already the terms where the delta xi when I and j are the same. They came here, and they gave you the second moment. Now I have the off-diagonal terms. But I have n of these guys and n minus 1 of these guys. That's why I have n minus 1. And let's see usual random walks. They have a similar effect. That means that n is fixed. Then x is the sum of delta xi till n, then x squared is sum over n delta xi delta xj average, n is fixed now. And here I have n delta xi squared. Then, as I said already, I have n plus n minus 1. Oh, I'm so stupid. And also you guys, 2. That's good that I'm checking this. It's obviously 2 because of the units, right? So, and again, if I, the off-diagonal terms here, I have delta x and delta x. So here I have delta x average squared. Usually what you measure is x squared minus the average of x squared. This is the variance of the random walker when you subtracted the mean. Like in uncertainty principle, you take the square minus the average to the power 2. This guy is equal to, it's very easy to see because this guy, you see you have n squared delta x squared. This is simply this guy. So when I subtract it, I get that this is equal to delta xi squared minus delta xi squared. So this is the variance of the microscopical jump, and the variance of the whole process with drift is simply n times the variance of the microscopical jump, as you expected. So this n minus 1 makes sense. But what is this n minus 1? It's not necessarily a simple thing, because this is related to psi. Again, I'm going to leave this for a calculation for you at home. So what is this n minus 1 average? This is the number of steps times n minus 1 number of steps. I'll just remind you how to get it. You need to sum over n from 0 to infinity n minus 1 psi s to the power n 1 minus psi s divided by s. This is the probability of getting n events. This is the average that you are calculating here. And this you do, you take this 1 minus psi s, divide by s, then you have psi s to the power 2, second derivative, of the sum, psi to the power n. Why second derivative? The first derivative will give you n. The second derivative will give you n minus 1. And then that's the reason why I multiply by this psi s to the power 2, because the second derivative will give you 2. This guy is simply 1 minus psi s. So you need to take the second derivative of this simple expression. And if you do that, you get that this guy is equal to the following: psi of s, all this to the power 2, s 1 minus psi s to power 2. This power 2 is easy to understand because when you take the second derivative, you get 1 minus psi s to the power 3, but then you multiply it by this 1 minus psi s. Essentially, this is it. So we have this guy, we have this guy in S space. So, and again, this is not related to power laws. It doesn't matter what it is. This is general. If you want, and this will be a homework assignment, you can plug in, let's say you have bias diffusion where this is not 0 and this is also not 0. You just need to take the small s expansion, look what is the small s behavior, and then you transform it back to real time. That's the technique. Always you go to small s, then you go to large T. Okay, so now I think we will stop here. In the next lesson, we will continue with this continuous time random walk a little bit more. We will look at what is the full distribution. The question is, why should I look at the full distribution? There are two answers. A, because I like it, and I like the math of it. But there is a deeper reason, and that is, when you have all this anomalous diffusion, you are confronted with kind of a problem, because let's say I calculated or measured this time of flight experiment. Let's say I measure the current is going like alpha minus 1. Okay, it's great. It's really, really amazing victory because of its wide applicability and because it deviates from everything you studied in high school, etc. It's interesting because it took you 4 years until you understood that Kirchhoff is not right. So it's very beautiful. I'm not underestimating this achievement. But the question is, when you have normal transport, you have all kinds of universal laws, right? What do I mean by universal laws? You have Ohm's law is universal. It's well applicable for everything. You have the Gaussian center limit theorem. It's well applicable for many systems. You have normal diffusion, okay. The diffusion constant is everywhere. Now you get this alpha. So you measure, let's say you measure this x average goes like t to the alpha. But alpha itself is not universal. So many people say, okay, it's not universal, that's life. It's interesting because then you have different systems, different alphas. Each system has a story. Sometimes it depends on temperature, sometimes it depends on other things. That's life, okay. But we want to show next lesson by going to the propagator that Px sum t, at least in this model, this guy is what is the universal thing. It still depends on alpha. So, but this distribution is not going to be Gaussian. It's going to be related to Levy statistics. Okay, I'm going to tell you the story, because I'm sure you cannot wait till next week to hear the answer. So the universality is in the propagator. The propagator itself is going to be related to Levy central limit theorem. Not because the jump sizes are power law like Levy flights, not because of that, but because the waiting times are power law. And then you have some type of universality that this density of particles is related to the generalized central limit theorem due to Levy, and not, some jungle out there. There is a jungle in the sense alpha is varying from different system to the others, but the universality is in this thing. Not only in this thing, but also in the measurements of currents that I mentioned before. You have this alpha minus 1 and minus 1 minus alpha. That's also something that repeats itself in many, many simple systems. All this type of philosophy, I don't know if you appreciate or not. The question is, what is physics? Because is physics related to some laws that are very individual for different systems, so each system has different alpha? Or do we emphasize the generalities that are repeating in many, many systems? Some people say we should only repeat, only discuss the generalities that happen in many systems. Other systems say, people say the opposite. If you have something that is changing, then it's interesting. It's a matter of philosophy, but we want to claim both. We claim it's A, interesting, and B, universal, but universal depending on what exactly you mean by universal, and this is related to this density that we will derive next week. Okay, so I guess I'll see you in a week from now. Please hand in your exercises that I gave you today, next week, next Sunday, because we are approaching the end of the semester, so I would like to finish not too late. I want you to go into the exam season with no pressure of doing these exercises. Okay? So next week, please hand them in. See you then.